Hi, everybody. So in this video, we are going to move into section 1.2, which is the second section of limits, and we're going to look at the idea of algebraic limits and then talk about an idea called continuity. So let's get started. Just like in the last section, before I get into what algebraic limits are, I do need to review the idea of factoring with you because there is a good bit of factoring in this section, and this is something you should have covered in an algebra class. But I did want to run through a couple of them that we're going to see a few times so you be more comfortable. So factoring, like number one, it says factor x squared minus 5x minus 14. So this is very common in just factoring trinomials. If you remember from algebra, you're trying to ask yourself what two numbers multiply to get negative 14 and add to get negative 5. So when that's the case, the only way you're going to be able to do that is to make it negative 7 and positive 2, because negative 7 times 2 is negative 14, and negative 7 plus 2 is negative 5. So we'll see a bunch of trinomial factoring in this class. Number two is the idea, let's see, factor 9x squared minus 49. So this is the idea of difference of squares. So if you remember from algebra, if you had a function in the form a squared minus b squared, you could factor that into a plus b times a minus b. So in this case, you notice that both of these terms are actually squared terms. So if you were to factor this, you would actually end up with the following. Let's see, what squared gives you 9x squared? Well, that would be 3x, because 3x times 3x is itself. So I'll write that down first. What multiplied by itself gives you 49? Well, that's going to be 7. So I'll write that down. And then difference of squares says one's got to be a plus and one's got to be a minus. So that factors into 3x plus 7 times 3x minus 7. And then probably the trickiest of the three is number 3, because being able to factor a trinomial where you have a number in the front. This is probably more comfortable for some of y'all than others. Some people catch this a lot quicker, but you're going to need to be able to factor a few things that have numbers in the front. So kind of going to the same idea, you can play around with your numbers here. And when you factor this, let's see, I'm going to try 3x and 2x, because I know that gives me 6x squared. And let's see, 5 and 1. Let's see, I would make this 5 and this 1. And it looks like that's going to be a plus here and a minus here. And way you can always check yourself is, remember, refoil it. If you need to multiply this back out by using your FOIL technique that you learned in algebra, do that, and you can verify that you do get the original problem. So as you're going through these factoring problems on your homework and such, make sure you're practicing double checking yourself, because you are going to see a good bit of factoring in the next, at least in this section. All right, so here's the nice thing. Algebraic limits, to begin with, aren't too bad. So here's the first definition. For any function f where a is actually in the domain of the function you're working with, then you can actually just apply the following formula. We can say that the limit as x approaches a of f of x is equal to capital F of a. So what that means is that if it's possible, and you can algebraically do this, you just need to take your a value and substitute it into the problem. So I picked out about 3 examples here of where you can see this. So number 4, the limit as x approaches negative 2 of x squared minus 5. If I plug the negative 2 into this problem, so that would be negative 2 squared minus 5, and you can either do this by hand or use your calculator. This is 4 minus 5, which is negative 1. And that's the answer to number 4. Same idea with number 5. If there's more than one x value, just plug it into both. So this would end up being 2 squared minus 5 over 2 squared minus 2, which would be 4 minus 5 divided by 4 minus 2, which is negative 1 over 2. And that is your answer to number 5. For number 6, we'll see a few radicals today, not too many, but don't treat it any differently. Plug your 5 in. This would be the square root of 2 times 5 plus 3, which is the square root of 10 plus 3, which is the square root of 13. So, and that is the basic idea of algebraic limits. Now, it does get a little trickier here in just a minute, but for the most part, this will always be our first instinct. Can we just plug the numbers in to get an answer? Now, there is an issue sometimes that runs into this, so I did want to show you this. Once again, if you need to pause the video to write this down, you can. But when you're working with a function where a is not in the domain of f, there are two options that you can do. Number one, you can simplify the rational expression, and if a is in the domain of the simplified expression, then you can redo the part we just talked about. If the rational expression does not simplify, or if a is still not in the domain of the simplified expression, then you can state that your limit at a does not exist. Now, some people get a little confused with those two rules right here, so I do have a kind of a quasi shortcut that might help you. So make note of this little statement right here. If you evaluate your function at a and you obtain the value 0 over 0, that is very popular to get in this section. This 0 over 0 form is a hint that a limit may exist, and you should look for ways to simplify algebraically to determine a limit in cases like this. So in layman's terms, 0 over 0 is not an answer. You have to keep simplifying until you get something other than 0 over 0, because we don't know what that represents. So let's look at number 7 and number 8 here. I want you to find the following limits. So number 7 says the limit as x approaches 2 of x squared minus 2x minus 8 over x squared minus 4. If you try to plug 2 into this problem, so you would get 2 squared minus 2 times 2 minus 8 over 2 squared minus 4, which is equal to 4 minus 4 minus 8 over 4 minus 4, which, let's see, that's going to be negative 8 divided by 0. Now, this is actually an okay answer to get. This is not 0 divided by 0. It's a number. We got negative 8 divided by 0. But as you learned in algebra, you can't divide by just a 0. So if you get something like this, it's fine. It just means that your limit does not exist. So that's an example where an algebraic limit would become DNE. Now looking at number 8, if you have the limit as x approaches 5 of x squared minus 4x minus 5 over x squared minus 2x minus 15, let's try to do the same thing here. If I plug 5 into all of the x's here, this would be 5 squared minus 4 times 5 minus 5 over 5 squared minus 2 times 5 minus 15. And if you try to simplify the top and the bottom here, you're going to end up, for the first time in this video, the fraction 0 over 0. Now, that is not an answer. You cannot stop here. What that is telling you is that the original problem should simplify in some way. So what I'm going to do here is I'm going to rewrite my problem. The limit as x approaches 5, and I'm going to try to factor the top and the bottom here. This is why we reviewed factoring a little bit earlier. If you factor the top, that becomes x minus 5 times x plus 1. If you factor the bottom, let's see, that's going to be x minus 5 times x plus 3. And what you'll notice here is that those two terms share an x minus 5 in common. So those would cancel, and you have a new problem to work. This is the limit as x approaches 5 of x plus 1 over x plus 3. Once you cancel the common term, you can then re-plug your 5 back into what's left over. So that would be 5 plus 1 over 5 plus 3, which is 6 over 8. And you do need to reduce your fractions. That reduces into 3/4 because they both share a 2 in common. And that is how you have to handle a limit when you get 0 over 0. Do not stop. You need to factor and simplify and then replug your value back in. All right. So remember from the last section that we talked about how you can find limits as x approaches 0. All right, well, this is going to bring us to kind of a new idea. So looking at this problem over here, the graph of 1 over x, if you try to do either one of the infinite limits, so the limit as x approaches infinity of 1 over x, all right? So as you approach infinity of 1 over x, you'll notice that the graph is getting flatter and flatter as you approach the x-axis. Well, the x-axis has a value of 0, so that means that your infinite limit here would be 0. You'll also notice, that if you approach the negative infinite direction, so as you go off towards negative infinity, the graph is also getting flat again at the exact same axis. So actually, your limit as x approaches positive and negative infinity of this particular function actually becomes 0. Now, why is that an important thing to note here? Is because we're going to need this following rule to do the next couple of problems. So in general, here's the rule I want you to note. If you take a limit as x approaches positive or negative infinity, it does not matter which one. If your function is in the form 1 over x to a power of p, and the power of p is greater than or equal to 1, then your answer will always be 0. Now that's a really easy thing to see from this problem, but we're going to see in just a minute or two where it's used on a bigger scale. So let's see that. For example, what if you want to find an infinite limit of a problem that doesn't have a graph for it? Now you could make a table here, but your table is going to end up being all kind of wonky and not the way we want to do it. So here's a different approach. I want you to find the following limits to infinity by dividing each term in the numerator and denominator by the highest power of the denominator. So this is an alternate way that you can do infinite limits. Is it the most popular? No, but it is an option that you can use. So let me show you how this works. Number 7. The limit as x approaches infinity of 7x plus 2 over 2x. All right. To do this method, since we are doing an infinite limit right here, all right, we can divide everything in the problem by the highest power of the denominator. Well, your highest power of the denominator is x. So I'm going to divide everything by x. So when I do that, it becomes 7x divided by x plus 2 divided by x over 2x divided by x. And we're going to simplify this. This becomes the limit as x approaches infinity of 7 plus 2 over x plus 2. What this now allows us to do is to use that property that we just went over. You will notice, and I can rewrite this one more time so we can actually see it. This is the limit as x approaches infinity of 7 plus 2 times 1 over x over 2. When you apply the infinite limit to the only term that's left, that has an x, you will notice that that is the form that we just talked about. We already know what this infinite limit is. That's going to go to 0. And since that's your only x term, you can now drop the limit off, and you're left with 7 plus 0 divided by 2, which gives you an answer of 7/2. And that's how you can do an infinite limit algebraically. It is a little tedious, and you got to be careful with all the dividing stuff, but this is another option that you can use when you're working problems of limit as x approaches infinity. Now, most people, like I said, don't use that method, but it does work. If you would rather go about it a more direct way, there actually is some rules that if you would like to memorize can make the problems go very quickly. So I'm going to read through these rules and we're going to apply all three rules on the next slide. So the limit properties can be used to show that if you have a function of a rational kind, so you have a bunch of x terms on the top and a bunch of x terms on the bottom, then the following has to be true. If you take the limit as x approaches positive or negative infinity of f of x, your answer will always be a over b if your power of m is equal to the power of n. So that essentially means that if your top power equals your bottom power, so you look at the highest power on top and you look at the highest power on the bottom, if they are the same thing, then you can just use the numbers that are right in front of them to give your answer. Now, what if one is bigger than the other? That's the next two rules. If the power of n is bigger than the power of m, so that essentially means that your top power is greater than your bottom power. That's fine. Your answer will always be 0 if that's the case. So if the power on the bottom, if the power on the, oh, sorry, I wrote that backwards. I apologize. Let me erase that. I meant to say bottom greater than top. Sorry, because n's bigger. If your bottom is greater than the top, then your answer is going to be 0 here. The top being bigger than the bottom is actually an easier case because it doesn't happen very often. But if your top power is bigger than your bottom power, so if m is bigger than n, then that just means your limit does not exist. So it means you can't do the infinite limit of problems like that. So we won't see that one very much in this class, but it is something to keep in mind if you choose to learn these rules this way. All right, so let me do an example of all of those rules we just talked about, and we'll talk through them together. So number 8, what is the limit as x approaches negative infinity of 5x squared plus 2x plus 3 over 3x squared plus 5? So when I do an infinite limit and you're using those shortcut rules, what I'm looking for is find the highest power on top and bottom. So in this case, both the top and bottom have the same x squared. That was rule number 1. If that's the case, you just use the numbers in front of those x squareds, and your final answer will be 5/3. Number 9 is exactly the same way. If you do the limit as x approaches infinity of x squared plus 2x plus 3 over 3x squared plus 5, find the highest power on top and bottom. So in that case, there's once again an x squared on the top and the bottom. If you use the numbers in front, now there is not a number in front on top, so that's understood to be a 1, and there's a 3 on the bottom, your final answer is 1/3. Number 10 and number 11 are the rules that go a little quicker because there's really no work involved. On number 10, same idea. If you read the problem out, you'll notice that your highest power on the bottom is x squared, while the highest power on the top is x. If the power on the bottom is bigger, your answer will automatically be 0. Versus number 11, if you look at your highest powers on top and bottom, there's an x to the 5th on top, and there's an x squared on the bottom. So make sure you note, if the top is bigger than the bottom, then your answer will always be D and E. Now, one thing to keep in mind with these rules is that these shortcut rules only work if your limit is x approaches either infinity or negative infinity. If x approaches some other number, you cannot do that in this case. All right, so now that we've kind of talked a little bit about algebraic limits, this leads us into the last part of this section, which talks about continuity or continuous functions, not another word for that. So when it comes to a graphical approach to continuous functions, this is actually a lot easier for most students to understand. So looking at these three graphs here in the first section, you've got a parabola, looks like an absolute value function, and then a logarithm function that we'll get more into later in chapter 2. But you'll notice that all three of these graphs are continuous functions. When I see a graph, when I think of a continuous function, I think, and I know this is going to sound very elementary wise, I think of what I call is the pencil test. Essentially is that if you can put your pencil at one end of the graph and you can draw the entire graph without picking up your pencil, then it is a continuous function. Now, there are a bunch of functions out there that are not continuous. So for example, I threw a few out here. If you look at these three graphs, there is some point on the graph that makes it not continuous, aka back to my pencil test idea. There is somewhere where you're going to have to pick your pencil up in order to draw the graph as it is. So you can see over here at x equals 3, they split up. I can't draw this without picking my pencil up. Even something as subtle as an open dot. I can't go and then jump over the dot and mark this one without picking my pencil up. So that's not continuous. And then the one we'll see a good bit of today, I believe, is this last one, where your graph is going to go up, then it's going to kind of jump down somewhere else and pick back up. When you see that gap there, you can't draw that spot without picking your pencil up, so it's not going to be a continuous function on the entire graph. So now if you have the graph, it's great. But what if you don't have the graph and you need a way to check if something is continuous at a certain point? So big definition here. A function f is continuous at a specific x value a if the following three things are true. If you can find f of a to exist, which means can you plug a into the original function and get an answer? If so, part A is good. Part B, you need to then do the limit as x approaches a of f of x and see if you get a limit value. So if you find the function to exist in part A and you find the limit to exist in part B, you're on the right track. But last but not least is part C. What you found in part A and what you found in part B, notice these are the same two things up here. They have to equal the same number. If they do not equal the same number, then that fails the definition of continuity. So you have to make sure that all three of these things are correct. Now, the last little part kind of goes back to the pencil test I was talking about. A function is continuous over an entire interval if it's continuous at every point. So as long as there's not a point where you have to say, pick up your pencil and go over it, you can say it's continuous over an entire interval. We don't do as much with this in this class, so I'm not going to stress too much about it, but I did want to put it there so you can have it in your notes. All right, so let's look at our first example here of continuity. Based on this graph on the right-hand side, I want you to answer these next 5 things. I want you to find the limit as x approaches 1 from the right, 1 from the left, and then the overall limit. Then I want you to find f of 1, and then finally part E, is this function continuous at 1, why or why not? So parts A through C is actually what we covered in the last video in section 1.1. Since all three of those are focused around x equals 1, let's find the right and left-hand limit. Now from the right, it looks like that your graph is approaching this closed circle that happens to occur at the y value of -1. So that would be your right-hand limit. If you approach 1 from the left, you are approaching this open circle, which occurs at the y value of 2. And as we learned in section 1.1, if your left hand and your right hand limit are not the same thing, that means your overall limit is going to be d in e. All right. More of an algebra concept, part D. What is f of 1? So back in algebra, when you evaluated functions off of a graph, all this asked you to do was to go to x equals 1, and f of 1 means you need to find the closed circle. So the closed circle is down here at y equals -1, so that would be your answer. So then the question becomes part E, is this function continuous? Well, obviously it's not because of the pencil test, because you can't draw this graph without picking your pencil up. But definition-wise, the reason that this graph is not continuous is because part C fails. Since the limit does not exist, this implies not continuous. So yes, I know if I get with the graph here, I could have answered this last question really quickly, but as you're going to see in a minute, I'm going to take the graph away and you're going to have to be able to answer this question again. So knowing these definitions does play a big role. For example, this one. Is the following function continuous at the indicated point y or y not? And we're going to do 3 or 4 of these because these are a big thing in section 1, 2. And you're going to see a bunch of these on your homework and quiz. So if g of x is 1/2 x plus 1 for x is less than 4 and negative x plus 5 for x is greater than 4, is this function continuous at x equals 4? Right? So your 3 steps of continuity we went over earlier. We're going to go step by step until they fail. Number 1, can you take g and evaluate it at the number that I give you? So can we find g of 4? Well, there's an issue here. Neither one of these inequalities has an equal to sign on it. And for a function value, as you learned in algebra, to work, you need an equal sign. Since there's not one, it is impossible to do this part. G of 4 is actually undefined here. You cannot plug 4 into either one. That means you can't do anything else. There is no need to go on to part 2 or part 3. If you cannot find G of 4, this means your graph is not continuous. Now, does this happen all the time? No, but I did want to show you because a lot of students will overlook part 1 and assume that it always works and then get the wrong answer. Always make sure both of your inequalities have an equal sign if the problem looks like this. All right, so here we go. Number 14, same instructions. If h of x is 1/3 x plus 4 for x is less than or equal to 3, and 2x minus 1 for x is greater than 3, is the following function continuous at x equals 3? All right, so part 1. Now we want to take x equals 3 and plug it into the function. So I want to know what is h of 3. Now, since there is an equal sign this time, you're going to plug 3 into the function that has the equal sign on it, which is the first one. That would be 1/3 times 3 plus 4, which would be 1 plus 4, which is 5, because the 3's right here cancel. You got an answer. So I'm going to put a check mark by it. As long as you get a number, part 1 works. Part 2, can you find the limit as x approaches the number in question, which is 3, of h of x? Now, since this is a less than and greater than problem, and you don't have the graph here, it's going to take a little bit more work. So what I would suggest you do here is we are going to break this up into 2 separate problems. We're going to do the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. Because remember, for the overall limit to exist, the left and right have to be the same number. Now, if you think of a number line here, I don't have the graph in front of me, but thinking like a number line. If x is less than 3, that is everything on this side of the number 3. That means 1/3 x plus 4 has to be your left-handed limit. So I'll put that one next to the left-handed limit. For x is greater than 3, that's everything to the right-hand side of 3. So I would put the 2x minus 1 next to my right-handed limit. And now you're going to work both of these separately. So that would be 1/3 times 3 plus 4, which we already did and got an answer of 5. If I do the same thing for my other function, this would be 2 times 3 minus 1, which is also 5. And from the last video, since the left hand and the right hand limit are the same thing, that means your overall limit is also that number, which is 5. So good job. Part 2 works. Part 3 says, and I always abbreviate this, and I'm okay if you do this too. Does part 1 equal part 2? Well, part 1, the answer was 5. Part 2, the answer was 5. So yes, part 1 and 2 were the same thing. So your final answer here is that this graph is continuous at x equals 3 because it met all 3 criteria that are required for that to be true. All right, let's do another one. Like I said, because I'm trying to do all the different ways you might see this. If f of x is x plus 2 for x is less than 3, 2x minus 5 for x is greater than or equal to 3, check is it continuous at x equals 3 again. Well, same 3 criteria. Number 1, can you plug 3 into the function as you did in algebra? So what is f of 3? Well, find the one that has the equal sign, which is the second one. Plug 3 into that. So that would be 2 times 3 minus 5, which is 6 minus 5, which is 1. And you got an answer. As long as you get an answer, part 1 is good. For part 2, you're going to do the limit as x approaches 3 of capital F of x. All right. But just like the last problem, since you've got less than and greater than, you need to break this up into a left and right hand limit. So let's do that again. This is the limit as x approaches 3 from the left, and we're going to do the limit as x approaches 3 from the right. Remember, left hand limit goes with the less than symbol because everything less than 3 is on the left hand side. So I'll put x plus 2 next to that one. X is greater than or equal to 3 is the right-hand side of that number, so I'll use 2x minus 5 for your right-hand limit. Plugging 3 into both of these, 3 plus 2 is going to be 5, and this one, 2 times 3 minus 5, we already found to be 1. Now here's the difference. Your left-hand limit and your right-hand limit do not equal the same number. And we saw that a few times in the last video. That's fine. That means that your overall limit does not exist because the left and right hand limit are not the same thing. That's actually bad when it comes to the idea of discontinuity. Since the limit does not exist, that means that your graph is discontinuous at x equals 3. It is not possible because you could not find the overall limit. All right, and then just like in the last video, I usually end most sections with a word problem or two to kind of show you where this applies, so let's do that. Number 16. The copy shop charges 8 cents per copy for quantities up to and including 100 copies. For quantities above 100, the charge is 6 cents per copy plus a surcharge K. If X represents the number of copies, the price function is as follows. Find K so that the function is continuous at X equals 100. So what you have to do here is, so as you can see, if you have 100 or less copies, so X is less than or equal to 100, they're going to charge you 8 cents a copy. If you get more than 100 copies, they're going to charge you a surcharge K, and then they're going to charge you 6 cents for every copy after that. We've got to find this K that makes this a nice continuous function. Now, as we just saw in number 15, the big issue is that if the limit doesn't exist, that's an issue. So I need these two values to equal each other when the domain starts to change. So what I would do on this kind of problem is I would take 0.08x and I need this to equal 0.06x plus k. Now, I can't solve this problem for k because I don't know what x is, but we actually do. At x equals 100, this is where you want it to be continuous at. So I'm going to take x equals 100 and I'm going to plug this into my equation. This would be 0.08 times 100 equals 0.06 times 100 plus k, which would be 8 equals 6 plus k. And if you move the 6 over to the other side, this means k would be $2. So for this function to be continuous, so if you were to graph it, which we're not going to, if you were to graph it and to guarantee that it would pass the pencil test I was talking about earlier, you need k, or you need your surcharge for this company to be $2. That ends the video for section 1.2, and that actually finishes our limit talks. So from here, we're going to move into section 1.3 in the next video, which is average rate of change.